All right, so we're going to do the viscosity lab today. We're going to be looking at 6 different petroleum fractions that come out of the distilling column, the fractionating tower. And we're going to be looking at patterns in their viscosity and patterns in their density, or to figure out if there are any patterns relating to their viscosity and their densities. Okay, so our 6 samples that we have kerosene or lamp oil. We've got a household lubricating oil. We've got mineral oil, motor oil, wax, paraffin wax. You can use this in the kitchen and cooking and other things like that. You can use this to seal, like melt it and then dip it a bottle in there and seal the bottle. And then a piece of asphalt. Literally from the parking lot, I went and found this, and it was very important. I had to find a piece that was big enough to fit into our graduated cylinders, because we're going to find the volume of this by water displacement. So I needed to be able to put it in here. All right, so I'm going to upload a picture of what these look like, because you need to write down the state of matter. So it's either a solid or liquid. We're going to have 2 solids, 4 liquids. And then you need to write the appearance. So what does it look like? What color is it? Does it have any other textural properties that you can see? That's probably going to apply more to the solids, the texture part. Okay, so I'm going to upload those pictures right now, and you can pause it to write down that data on your lab. Okay, so for this next part, we're going to be testing the viscosity. So hopefully from the pre-lab, you guys figured out that viscosity is, the definition is resistance to flow. So something that flows slowly or is syrupy, sticky, like honey or molasses or syrup, those things are viscous. So we're going to test to see the viscosity. So each one of our containers, our test, well, it's not quite a test tube, but our tubes has a bead in the bottom. And we're going to test how long it takes the bead to go through the liquid. Okay, so the faster it goes through the liquid, the least viscous it is, the less viscous it is. So if it takes longer to flow, then it's more viscous, if that makes sense. Okay, I know my grammar was not fantastic there, so forgive me. All right, so I'm going to test this. It's probably going to be easier for me to just take pictures. So I will test each one. I'm going to have to do it 3 times. All right, so I'm going to test each of just the liquids. We can't test the viscosity of a solid because it's a solid. So I'm going to test each one of the liquids 3 times, and I will take pictures of that and upload it. Just real quick, I'll show you how I'm going to do it. It says hold the capped tube containing the mineral oil. I'm going to start with kerosene until the bead is inside the, I'm just going to hold it right there so I can see it. It's up near it's touching the top part. I'm not going to go in the cap because, well, maybe I can. I just don't want it to affect the results because there's like a little lip on the inside. Anyway, I'm going to hold it horizontal. So the bead right now is in the cap part. All right. And then I'm going to quickly turn it upright, and I'm going to time how long it takes the bead to reach the bottom. Okay. I'm going to do that 3 times for each of my 4 liquids. So I'm going to do that 12 times, and I will insert a picture here. And you can. Okay, so now go ahead and calculate the average for each of the samples. So you're just going to add up the times for each one, and then because there's 3 times for each one, you're going to divide your total by 3, and that gives you your average. So add them all up, divide by 3. I did have to redo a couple of my trials, and that's really important to mention, because when you have a messed up trial, you can tell you messed up because the number doesn't match. It's not even close to your other numbers. So like kerosene, I had 0.60, 0.72, and 0.65. So if I got a number that was like 1.5, I would know that that wasn't a good trial because it's very different. It's about double the other numbers. So I would know something went wrong during that trial and I should redo it. I should not include that number in my average. I should redo it if I have time. So it would be an outlier. And we don't like those in science. We don't like outliers. We would much rather redo it so we have kind of more consistent data. All right, so then you need to rank the 4 liquids 1 to 4. So 1 would be the least viscous. So you're looking for 1 to be the one that has the shortest time, because that means that the bead made it from one end to the other without much trouble. It flowed easily. All right, the one that is the most viscous should have the longer time, and that would be the one that has, that's because it took longer for the bead to flow, like that one, man, that's slow, through the liquid, has resistance to flow, it's more viscous. All right, okay, let's move on to the density of the solids. So density of the solids, we're going to take our 2 solids. I'm going to put them on the scale and get their masses. Because remember, to find density, we need mass and volume. And then to find the volume, I'm going to put some water in a graduated cylinder, record the volume, then put my solid in the graduated cylinder, see how much the water rises, record that volume, and I'm going to subtract the 2 volumes. That's going to be the volume of the solid. And remember, that process is called water displacement. Okay, water displacement for that process there. Okay, and then we can go ahead and calculate the density. Remember, that's mass divided by volume. Okay. Okay, so we're back. To find the volume of those solids, you're going to want to subtract the larger number from the smaller number. Volume can't be negative. So subtract that and get the volume, and then you can find the density doing the mass divided by the volume that you calculated after you did the subtraction. Okay, so that will give you the density of your 2 solids. Okay, now moving on to density of the liquids. Now, our conundrum is we cannot just open this up to get the liquid out and measure the liquid because that would make a mess. And some of these oils are very, very, they have a lot of fumes. They're very smelly. Okay, so we do not want these fumes in the classroom. So we can't open those up. So what we can do is, and we can't take them out to put them on the scale because they're a liquid. So we've got to be a little creative here in figuring out the volume and the mass of these liquids. So I have, we've got one that's empty that just has the bead in it, and it's the tube and the cap. So we can use this. I'm going to put this on the scale. We're going to get the mass. Okay. And then I can get the mass of all my other samples. And then I can subtract those 2. And if I take these and I put them on the scale, okay, and if I subtract them, then I will be subtracting, it's just the empty one, I'll be subtracting the mass of the tube and the cap, and I will be left with just the mass of the liquid inside. Okay, so we're going to do that to get the mass. To get the volume, we need to, I have a tube and a cap with water inside. And we know the density of water is 1. Okay, so if I can get the mass of the water and I know the density of the water is 1, I can work backwards to calculate the volume. Sounds a little bit complicated, but it's really not that bad because the density is 1. So that means that the mass equals the volume. So when I find the mass of the water, I will also know the volume of the water. And then I can assume, because this is full, along with the other 4 samples that are liquids, this is full and it's the same size, so the volume of my water should be the same volume for each of my other samples. They're going to have different masses, but because the container is the same, the volume, we're going to assume that the volume is the same for each of our liquid samples. Okay, so when we find the volume of water, you can go ahead and record that volume for the 4 other samples, because all the volumes will be the same. Okay? Okay, so you should be done with water now. What you're going to do is you're going to take your mass that you got here, well, that I got, mass that I got here, we're going to subtract this, the empty tube, from the filled tube. We're going to get the mass here of just the water. That mass is going to go down here. So determine the volume of the liquid inside the sealed tubes. We'll use what we know about water. We know that the density of water at room temperature is 1 gram per milliliter. Use the mass and density of water to determine the volume of water in its sealed test tube. Show your work. So the formula for density is mass divided by volume. We can rearrange that. Look at the triangle here. If we're solving for volume, then we're going to do mass divided by density. So we're going to use this mass that you got here. That's going to come down here. We know the density is 1. So it's going to be volume equals whatever mass you got divided by 1. Remember, anything divided by 1 is itself. So the mass and the volume should be equal. That's kind of a nifty thing about water, is that 1 milliliter of water is 1 gram of water. So that's pretty cool. Okay, now that number that you got, you're going to take that number, and that is going to be this volume here. So on the next page, your volume that you got for water is going to be the volume for all your other samples as well. Okay, so assume that the volume of water in its test tube is the same as the volume of each petroleum product in its test tube. Okay, so I'm going to go ahead and fill in the masses of these. The empty tube and the bead is the same mass all the way down. Should be the same as we got for water, which was 29.21. So I will fill that in, and then I will go ahead and get the masses of these, and I will be back with another picture. All right, so now you have the mass of your test tubes, or mass of our products. We can just subtract this minus this, and that will give you the mass of what's inside for the 4 liquids. The volume that you got from water, which is 30.29, heads up. So you're going to do the mass divided by 30.29, and that gives you the density for each of your liquids. And then you're going to rank them from least to most viscous. You've already done that. We ranked them 1 to 4 in the data table, so you're just going to write them here. 1 is least and 4 is most. Number 2, rank all 6 of our products based on the density, least dense to most dense. So now we're going to look at this density here in this table, and we're going to look at the density of our 2 solids, which was the asphalt and the wax, the paraffin wax. Okay, so look at those 2 densities there. And you're going to compare all 6, put them in order, okay, based on least to most. All right. Number 3, look back at your data table for appearance and compare the number of carbon atoms to the viscosity. So this is just going to be on the liquids. Propose a rule based on your observations in this investigation about the connection between the number of carbon atoms in a substance molecules and the viscosity of the substance. So let me show you where to look. So back in our very first data table for appearance and state, it says the number of carbon atoms per molecule. Okay, and I went ahead and I put them in order from least to most. So does your ranking of viscosity from least to most match the number of carbon atoms from least to most? Does that match? Is there a pattern? Does the one with the least number of carbon atoms is it also the least viscous? Or is it the most viscous? And does it go backwards? Okay, so what is the pattern there? And is there a pattern, and what is it? There is a pattern. You should see a pattern. Okay? Then number 4, you're going to use that same number of carbon atoms in that first data table, but this time you're going to look at the densities. And is there a pattern from least to most dense? going along with the number of carbon atoms in each substance. Okay, so does the density pattern follow this order? Least to most dense, is it in this order or is it not? Okay, hint, no, there's no pattern. Okay, number 4 is no. Okay, all right, that's it. So make sure you finish up your data tables, finish up the answers there, and send that to me, and then take the Canvas quiz. Okay, good luck.